Whether it's the touchscreen on your phone, the smart windows in modern buildings, or the next generation of perovskite solar cells, there's this hidden layer of magic making it all work. We're talking about transparent electrodes. Today, we're going to break down the physics, the incredible materials engineering, and the cutting-edge future of these invisible powerhouses.
Here's our roadmap for today. We'll start with the window wire paradox, look at how TCOs actually work, see how they power perovskite solar cells, meet the current TCO heavyweights, check out some next-gen electrode alternatives, and finally, look at the future of solar.
Section 1. The window wire paradox. How can glass conduct electricity?
To really appreciate transparent electrodes, you have to understand that what they're doing shouldn't really make sense mathematically based on everyday materials. We're literally asking a material to do two completely contradictory things at the exact same time. Look at this comparison. Over on the left, we've got glass. Glass is fantastic at letting light pass through, right? High optical transparency. But if you try to run an electrical current through it, absolutely nothing, poor conductivity. Then, on the right, we have metals, like a copper wire. Metals are brilliant at collecting and transporting charge carriers, excellent conductivity. But you definitely can't see through a brick of copper. A transparent electrode has to somehow fuse these two extremes together perfectly.
And for a technology like a solar cell, the requirements are just incredibly strict. To even be workable, a transparent electrode needs an 80 to 90% transmission rate in the visible spectrum. It also requires a super low sheet resistance, specifically under 10 ohms per square, which just means the thin film won't lose the electrical current as heat. It needs the right work function, which is the exact amount of energy needed to extract an electron, so it aligns perfectly with the other layers in the cell. Plus, it has to survive extreme moisture, oxygen, UV light, and thermal stress. Add in the need for mechanical flexibility for modern tech, and oh yeah, it has to be cheap enough to actually commercialize. It's a massive, massive engineering checklist.
Moving on to Section 2, how TCOs actually work, the physics deep dive.
So how do engineers solve this paradox? They use Transparent Conducting Oxides, or TCOs. And to understand how these work, it all starts with a concept called a band gap. In physics, a band gap is basically an energy threshold. Think of it like a hurdle that an electron has to jump over to go from being stuck in place to being excited into a conductive state where it can actually flow as electricity. Now, pure metal oxides naturally have very large band gaps, which normally makes them strictly electrical insulators.
But here's the cool part. That large band gap is exactly the secret to their transparency. TCOs have a band gap energy of greater than 3 electron volts. Now, think about sunlight for a second. The visible photons raining down from the sun only carry about 1.7 to 3.1 electron volts of energy. Because the incoming visible light simply lacks the 3 electron volts required to even interact with the electrons in the TCO, the light can't be absorbed. It literally sails straight through the material. And boom, that gives us our high transparency.
But remember, pure oxides are insulators. We still need this stuff to conduct electricity. We do this through a process called doping. Let's use indium tin oxide, or ITO, as our example. Engineers start with the insulating oxide and they introduce doping. Specifically, they swap out an indium atom, which has a 3+ charge, with a tin atom, which has a 4+ charge. That tiny calculated chemical substitution physically generates a free extra electron. You multiply that across the entire material and you achieve a massive carrier concentration. That gives you metallic-like conductivity right inside what is basically a transparent window.
Section 3. Powering perovskite solar cells, building the architecture.
Okay, so we've got this incredible material. How do we actually use it to generate power? Well, a standard NIP solar cell structure is built vertically, layer by layer. We start with a glass substrate. Right on top of that sits our transparent electrode. Then comes an electron transport layer, like titanium dioxide, to funnel negative charges away. Next is the absolute star of the show, the perovskite absorber itself. Finally, we cap the whole thing off with a hole transport layer to pull away the positive charges and a solid metal electrode at the very back. Sitting right there at the front of that stack, the TCO has an absolute non-negotiable dual function. First, sunlight enters through the glass and has to pass right through the transparent electrode to hit the perovskite. If we just used a standard metal for this front contact, the light would be completely blocked, and zero power would be generated. But at the exact same time, once the perovskite absorbs that light and frees electrons, the transparent electrode acts as the current collector. It grabs those electrons and pulls them out to the external circuit. It's the ultimate gatekeeper for both light entering and power exiting.
Which brings us to Section 4, the current TCO heavyweights, FTO, ITO, and AZO. Because this role is so absolutely critical, these materials are fierce competitors in a high-stakes race trying to balance efficiency, stability, and commercial cost. Here's how the heavyweights stack up. First, FTO, or fluorine-doped tin oxide. It offers good transparency and conductivity, all at a really low cost. Then there's ITO, indium tin oxide. This is your premium choice. It has the absolute highest transparency, somewhere between 85 and 95%, and excellent low sheet resistance, but it is very expensive. Finally, we have AZO, aluminum-doped zinc oxide. It's a low-cost, non-toxic alternative, but you trade off with slightly lower, more moderate conductivity.
Now, while ITO might look like the winner on paper, FTO is actually the most common choice in laboratory perovskite solar cells, and here is why. 500 to 600 degrees Celsius, FTO has excellent thermal stability. You see, in solar cell manufacturing, adding layers like titanium dioxide often requires high-temperature sintering. FTO can survive this intense heat without melting or degrading, which basically makes it the rugged, dependable workhorse of the entire industry.
And this brings us to the fatal flaw of the reigning champion, ITO. Despite having the very best optoelectronic performance, ITO relies heavily on indium. Indium is a rare element which creates massive global supply concerns and drives the cost way up. But even worse, ITO is incredibly brittle. If you try to physically bend it, it completely cracks. And as we look toward a future of flexible, wearable solar panels, well, a brittle electrode is completely useless to us.
Section 5. Next-Gen Electrode Alternatives, Agile New Challengers. So, if traditional metal oxides are too brittle or rely on rare earth elements, what is next? Researchers are working tirelessly to unlock true mechanical flexibility. Look at this landscape of alternatives. We've got silver nanowires, graphene, carbon nanotubes, and conductive polymers like PEDOT. Across the board, every single one of these scores excellent in flexibility. They can survive thousands of bending cycles without breaking a sweat.
Silver nanowires are actually one of the strongest candidates right now for flexible commercial cells. They offer up to 95% transparency and are fully compatible with continuous roll-to-roll manufacturing. Literally, think about printing solar panels like newspapers. But there are still engineering hurdles. Silver can oxidize and degrade over time. Plus, imagine microscopic sticks piled on top of each other. The spots where these wires intersect add junction resistance, and their physical roughness can actually puncture the ultra-thin layers of the solar cell. Then there's graphene, a single atom-thick sheet of carbon. A single layer of graphene offers a staggering 97.7% optical transparency. That's wild. It's exceptionally flexible, chemically stable, and lightweight. However, right now, taking this miracle material from the lab to large-area commercial fabrication is just a massive challenge. Transferring large sheets of it often results in microscopic wrinkles and cracks, which creates high sheet resistance.
Let's wrap things up with Section 6, the future of solar, hybrid horizons.
So with traditional TCOs being too rigid and the new alternatives having their own manufacturing quirks, where is the industry definitively heading? Well, the crucial takeaway here is that the field isn't just looking for one magic material anymore. They're combining them. The cutting-edge trends are focused on entirely indium-free systems, unlocking flexible and wearable formats, and building tandem cells that stack perovskite right on top of traditional silicon. To pull this off, researchers are aggressively moving toward hybrid electrodes, fusing the best properties of multiple materials together. Think combining graphene with silver nanowires, or putting a metal mesh together with a TCO. In fact, the expert consensus strongly suggests that this hybrid approach is the ultimate future of solar power. By laying down a highly conductive, flexible network, like silver nanowires or carbon nanotubes, and then coating it with an ultra-thin oxide layer, you solve the brittleness of ITO while also fixing the surface roughness of the nanowires. You get the best of everything: high transparency, low electrical resistance, and incredible mechanical durability, all in one single package. Which leaves us with this final thought. We have spent decades trapped by the physical limitations of rigid glass and brittle metal oxides. But with hybrid transparent electrodes stepping into the spotlight, is the era of shattered screens and stiff, rigid solar panels finally coming to an end? As this invisible technology leaps forward, we are rapidly approaching a near future where clean energy can be seamlessly printed, dynamically bent, and even worn directly on our clothing. Thanks for joining me for this explainer, and keep questioning the science around you.